So we're going to go through the PowerPoint first. And here's where the algorithm comes from. So there's the product rule from section 3.3. If I want to differentiate this product, so they're calling the functions u and v, doesn't matter what they are. You remember how to do this. You take the first term, multiply it by the derivative of the second, plus the second term times the derivative of the first. That's the product rule. It's just another way of writing the same thing. Okay, and this is where it starts in your textbook on page 341. So now what? Algebra 1, we just added negative v d mu to both sides. Now what was on the right, they rewrote on the left. What was on the left, they rewrote on the right. So now what you're going to do is you're going to anti-differentiate both sides. So you anti-differentiate both sides. On the right side, you give each term, on each side of the subtraction sign, their own integral. And you get this. So the left side's the question. It is the integral of u dv. And what's that going to be equal to? U times v, subtract the integral of v du. And that's going to look like just a mess to you, like, well, what does that even mean? So you see an example, okay? But this is what you're accountable for. This is the algorithm. You could always do this if you don't remember it. You could rewrite the product rule and do what was on the screen. None of it was complicated. It was just algebra 1. But the problem is that's going to be a time sink for you to do that. Okay. Well, here comes a decision. Which one do I call u? Which factor do I call u? And which one do I call dv? And it's possible that if you choose this wrong, when you identify which one's u and which one's dv, that could take you to a dead end, and you'd have to back up. All right, so you want to be careful. Take your time before you decide which term is which. So this is on the PDF. They're saying this is what you should call u. In this order, they have this mnemonic. I never really found this helpful, but sometimes people do. So if you have a log there, then that would be your u term. Inverse trig, your u term. And from there. Okay. So here's an example. You want to anti-differentiate this x cosine x dx. You have this product. And if you look at this thing, we can't do this by substitution. That was section 2 in chapter 6. There's nothing here to do by substitution. It doesn't lend itself to that technique. So here's the algorithm, right? And you say, okay, well, that's a polynomial, the x. Well, what you notice is that's going to differentiate to 0 eventually. So you call that u. So that means the other factor, which is cosine x dx, would be your dv, meaning that is already, this thing right here represents the derivative of v. So here, you differentiate. What do you get? d mu dx is 1, so d mu equals dx. For this term, for this column, we're going to anti-differentiate. So cosine x dx is the derivative of sine x. So you went two different directions here. In this column, you differentiated. In this column, you anti-differentiated. Now you're just going to substitute in the algorithm. Ready? You would get, we're just looking at, here, you're only looking at the right side here, what it's equal to. So the question was, anti-differentiate the x cosine x dx. So the question is up here, this top line, this top row. This is the answer. U times v, x times sine x, subtract, anti-differentiate sine x dx. Well, see what you've done here? This thing can be anti-differentiated. You're going to have to apply this again. You're going to have to do another step. But this can be anti-differentiated, where that couldn't be. So you would end up with this. What is sine x? Sine x is the derivative of negative cosine. So this would anti-differentiate to subtract a negative cosine, and then you have to add the c. Okay? So if you were to take the derivative of this, you would get to x cosine x. You anti-differentiate it. How would you differentiate this? You would do the power rule. You would do the product rule. Right? And you would have the sum of these two terms. Here's another example. Ready? You want to anti-differentiate this. Just substitution is not going to help you. So there's the algorithm. You get a log in there. So we're going to call this term the u, and then dx is our dv. In the first column, we're going to differentiate. In this column, we're going to go the other direction. So the derivative with respect to x of ln x is 1 over x. If dv equals dx, when you anti-differentiate it, v equals x. Now we're just substituting them. Again, what they're rolling out here is just the right side of the equal sign. This top row is the question. Anti-differentiate the top row. And then the answer, you're just substituting. You get to plug it in. ln x times x, u times v, subtract v d mu. What's that going to give you? Well, you have x ln x, commutative property multiplication. Subtract what? Well, this is 1. Okay, this reduces to a 1 dx. So it anti-differentiates to x with respect to x, and that plus c. So again, if you took this, your answer, and differentiate it, you get back to the question. You need to do this. You need to come back to this PowerPoint and go through this at your own pace. So you're doing a problem from the exercises. You open up the PowerPoint and you go through that. You compare it to the problem you're doing. So this says example 4 on the PowerPoint, but in your textbook, it's actually example 2. All right, so we're going to do this problem here and then send you to do a problem that maps onto it, okay? So there's the algorithm. So u equals x squared. Now we're going to do the rest of the term is dv. First column, we're going to differentiate. d mu dx is 2x, so d mu is 2x dx. dv, we're going to anti-differentiate, but e to the x is its own derivative. So now we got to substitute. You see where they're getting this? this diagonal product, subtract v e to the x times d mu. Except what? Well, all you really did here is you changed your question from having x squared ex to be integrated to, instead of x squared, 2x. You bring the 2 out, and you still have to anti-differentiate that integral. So you need to reapply it. So we just set aside this whole thing. Set aside x squared e to the x, subtract 2 times, and you do this question over again. Anti-differentiate x times e to the x. So this is like what was up at the top, except instead of u being x squared, use 2x. Now they factored the 2 out front. It doesn't, so it's really x if you factor that out there. Differentiate, anti-differentiate. And you see what happened? Everything now is outside of the integral symbol except e to the x, but you can anti-differentiate that because it's its own derivative. And you would have this first term, ready? Distribute a -2 over what's outside the integral symbol. And then you have a -2 times the opposite of this. A negative times a negative is a positive, and you would have 2 e to the x plus some constant. All right, so the issue is, in this example, you had to do the integration by parts twice. Right? And that's what the problem is going to be like that we're going to send you to. So the same work here on the PDF that you just saw. Okay. So I said, okay, here's the way we have this. I didn't write it the same way. I wrote this as a row, what they wrote as a column. All right. So I have u equals x squared. There's d mu dx. So I just worked across. And the other term from the question is e to the x dx, and that gets anti-differentiated. So their blue table, there's 2 of them, because you had to do it twice, and you would end up with this, okay? So if I go to the calculator, I go to y equals. Right? So I'm putting my answer in y1 for this example 2. I'm putting the question in y2, and I'm turning on when I have the derivative in y6. It doesn't, you have it in there, one of your lines, okay? Now we're going to see if we differentiate y1, we take the derivative of our answer, which is our integral. After we integrated y2, do we get back to the question? That make sense? And the tables match up. Okay? The tables match up, which is confirming that you did what? When you take the derivative of your answer, you get back to the question. So you've used this technique before with your calculator. And what we're going to do is leave this up here. All right. And that's your model for you to go to problem number 5. All right, so let's take a look at 5. And you want to have, you know, this routine of setting the problem up. So I'm saying u is x squared, and as I went, my row here was the PowerPoint column. I don't mean to confuse you, but it's also easier to see the whole problem in one sheet if we use rows here. Then dv is cosine x dx. When you anti-differentiate that, you get sine x. So what do you have out front? You have uv subtract the antiderivative, ready, of v du. And I took the 2 out front, just like they did on the PowerPoint. Okay, what did you do? Well, you took the original question and you reduced the degree of x by 1. It went from x squared to x. So you can see how you're going to do this again, where u is x instead of x squared. So you're going to have this first pair of factors subtract everything over here. So when you do that, you would get, ready, u v. You get a negative x cosine x, subtract the antiderivative of v du, and that cosine x, subtract the negative. This cosine x dx will anti-differentiate. That's a derivative sine. Okay, so you get this term here, right, plus what? Well, it's plus 2 because this was, I was subtracting all of this. When you're subtracting a negative, so that 2 gets distributed over everything, you would have plus 2 x cosine x, right? And then this thing is sine x, but you're distributing a subtraction over that. So you subtract sine x plus the constant. Okay, don't forget the constant. And the this step between here and here, all I did was distribute the 2. You don't need to do that. If this is an FRQ and you left it like the top one, it's 100% correct. Okay, now, so that's it for the alpha lesson.